In today's lesson, we're going to be looking at optimization. For the following problem here, starting off this idea of optimization is we have two numbers whose product is 10,000 and whose sum we want to be a minimum. Obviously, there's a lot of different combinations of numbers whose product is 10,000, but we want to find those numbers where the sum of those numbers is a minimum. So to solve this using our optimization methods in calculus, we have to set up an equation to represent both of these conditions. Equation number one will be x times y equals 10,000, where x is your first number and y is your second. And the second equation is we want to minimize x plus y. Now you can write this as a multivariable function as follows. Whenever you want to optimize a function, whether it's minimizing or maximizing, you can't do that with multivariable functions. So therefore, what we need to do is convert this function to a single variable value function. To do so, we're going to examine our first equation and isolate for x and substitute that in. Let's go ahead and isolate for x. So now you see I've isolated for x and I substituted that into our multivariable function, turning our function into a single variable function, and now we can discuss the idea of minimizing or maximizing. So now we have a single variable function and we want to minimize this. To do this, we take our first derivative. Taking our first derivative, we get the following. And then I just went ahead and got a common denominator here and set this equal to 0 so we can find our critical numbers. Critical numbers exist where the function f prime is equal to 0. This happens at the following points. This happens when y equals plus or minus 100. Substituting this into our equation 1, we have the following two x values. So solving for x here, we get that when y is 100, x is 100, and when y equals minus 100, x is minus 100. These are two local minimum points. Since we want an absolute minimum, we're going to go ahead and choose this value here. So the answer for this is when x equals minus 100 and y equals minus 100, the product is 10,000 and the sum is a minimum. All right, let's take a look at another problem here. So in this problem here, we have 2,700 square meters of material that we want to use up. And what we want to do with this 2,700 square meters of material is we want to make a box with a square base and an open top on that box, and we want to find the dimensions that will maximize the volume. So let's go ahead and draw ourselves a diagram and try to calculate the surface area of a box with a square base and open top. So you see here I did a quick diagram of our square base. Notice because it is a square base, I labeled the bottom here the same dimensions and then some other variable y for the height of the box. So to calculate the surface area, we have to break this up into its faces. You'll notice when calculating the surface area of this box, the front, back, left, and right all have the exact same dimensions. So the surface area of those will just be x times y. And the bottom of the box is, and we're just have it's an open top, so there is no top to this box here. And the bottom of this box is just going to be x times x. So the total surface area of this will be 4xy plus x squared. Now we know in the question this is equal to 2,700, so let's go ahead and equate that. Now we want to maximize the volume. Expressing the volume of this function, this will be a multivariable function again, so the volume as a function of x and y will be length times width times height. So in this case here, it'll be x squared times y. And again, we can't maximize a multivariable function, so we have to go ahead and isolate for one of these variables and solve for x. You can see here it's much easier to isolate for y than it is to isolate for x. So we're going to go ahead and isolate for y and sub that into our volume equation. So you can see here I isolated for y and I substitute that into our volume equation. Now we have a single variable function. We can talk about maximizing or minimizing a single variable function. And you can see here I canceled off the x's. You just assume x can't be 0, which it obviously can't be because it's a length. So now to maximize this, we want to go ahead and take the derivative of this function. So I'm going to go ahead and distribute the x first, simplify this up a bit, and then I'll take the derivative. Doing so, we get, now that I've taken my derivative, we're going to set this equal to 0 and solve for our critical points. Doing so, we get, setting this equal to 0 and solving for x, here you can see we end up getting x squared equals 900. Taking our square root, we get x is plus or minus 30. Obviously, length can't be negative, so the only possible value here is x is 30. We need to examine the domain of the function v at x, making sure this is actually within our domain. So let's get some restrictions on these values here. In this case here, x has to be greater than 0, and 27 minus x squared must also be greater than 0. So taking a look at this inequality here, we have 2700 minus x squared must be greater than 0, or x squared must be less than 2700. Giving us x must be less than 30 root 3 after we take our square root. So therefore our x value has to be strictly greater than 0 and less than 30 root 3. Now, we can't actually have x being 0 and x being 30 root 3 because that would just give us volumes which are 0. But we can use those as the endpoints because they still are technically defined. So we'll actually include the 0 and the 30 root 3 in there. So we have a critical point and we have two endpoints. Let's go ahead and check these in our volume function right here and choose the largest. So as we discussed, the volume at 0 will be 0 and the volume at 30 root 3 will be 0. If you evaluate the volume at 30 right on, you get 13,500. So therefore, our critical point, checking the endpoints, its largest volume at the critical point of 30, so we have a maximum when x equals 30. Substituting this in and solving for y, we get y equals 450. So therefore, creating a box, which is 30 by 30 on the base and a height of 450 centimeters, will yield the largest volume.